Training large language models efficiently is one of the biggest challenges in AI right now. From Microsoft Research Cambridge, Chow and Wenbo introduced adaptively rotated optimization, or ARO, a new approach to optimization that uses geometry-aware updates to significantly improve training efficiency at scale. This is fresh work coming straight out of the lab, with timely results and big implications for both research and production systems. Handing it over to you, Chow and Wenbo.
Hello everyone, my name is Chama and I'm a senior researcher at Microsoft Research Cambridge. We have been working on innovations in AI efficiency, and together with my colleague Wenbo, we'll talk about ARO, the new matrix optimization framework for large models. This has been a collaboration with an amazing team at MSR Cambridge. To begin with, training AI is expensive, and the optimizers crucially determine how effectively they turn compute into intelligence. The industry so far has been dominated by the use of Adam for a decade. Now, matrix-based optimizers like Muon are emerging using gradient orthogonalization methods to improve sample efficiency and supporting production-scale training. From our perspective, we believe orthogonalization as one example of this new optimization research landscape. And the goal of our work is to develop new paradigms in optimization that push the efficiency frontier even further. To explain our approach, let me start with the basics. Gradient descent is the simplest optimizer. It computes a gradient G and uses it to update the weight W. Adaptive optimizers like Adam also follow the gradient, but they adaptively rescale the gradient before applying the weight update. The adaptive rescaling is implemented by some nonlinear mapping, F. And more recent matrix optimizers like orthogonalization, shampoo, and soap, etc. are more complicated. However, despite very different motivations and derivations, they are fundamentally similar to Adam. After some simplifications, we can show that they run Adam-like optimization, but in a rotated coordinate system. Concretely, this happens by first rotating the gradient by R transpose, then apply the nonlinear map, F, in that rotated basis, and finally rotating back. In the literature of matrix optimization, F is typically variance of Adam, and R is chosen as the single vectors of G. This reinterpretation is not entirely new, but based on the insights from our research, we believe rotation should not just be a reinterpretation, but instead a core primitive principle for optimizer design. This perspective opens the door to many new ideas in optimization, and in particular, we propose the use of more powerful nonlinear mappings beyond Adam's rescaling, and more significantly, better rotations that are informed by the choice of F and deliver improved sample efficiency. And that gives our framework adaptively rotated optimization, or ARO. Before going to the details of ARO's performance, let me first comment on why we believe rotations are so important. We hypothesize that it is really rooted in symmetries of the loss landscape. Current language models architectures choices for sample transformers have rich rotational symmetries in their weights, which, when applied correctly, those rotations will leave the model's predictions unchanged. ARO exploits this property by moving along those symmetry orbits without changing the model's output to search for updates that are more effective at navigating the loss landscape. And this symmetry hypothesis also enables additional features of ARO, for example, leveraging cross-layer couplings for better performance. In summary, ARO is a general optimization framework that not only explains many existing matrix optimizers, but also enable the discovery of new update rules that work very well in practice. Now, I will hand over to Wenbo, who will walk through our key results.
Thanks, Chao, for introducing ARO. Hi, I'm Wenbo. Since we have covered the key features of ARO, next I will briefly talk about how it performs in practice. To ensure fair comparison, we have carefully built an optimizer benchmark protocol that aims to mitigate many potential forms of evaluation bias. First, we collaborated with Microsoft Research Asia and evaluate the error on their newly developed MOE model called Sigma. We measure the optimizer performance using the relative speedup in steps over AdamW. This is shown in y-axis, and the x-axis indicates the data scale, where each unit represents the chinchilla compute optimal dataset sizes. For example, this spot indicates the 1.36 times speedup at the 8 overtrain factor. It means that ARO only uses about 73% of the data or GPU time to reach the same loss as AdamW at that training stage. Therefore, the higher the speedup, the more efficient the optimizer will be. From the plot, we can see the result forms two clusters. The lower cluster represents orthogonalization-based method, including mu1. The upper cluster shows two ARO variations. Their results shows a clear performance gain for ARO, which persists across data scales. Importantly, ARO can optionally be used as a full model optimizer, where all matrix parameters in the model are updated under a single rule. While some orthogonalization methods, although we do not show it here, can be unstable in that setting. Overall, this suggests ARO converges faster and delivers better sample efficiency under our rigorous benchmarking protocol. Next, we stress test ARO across model scales to check whether its efficiency gain holds as we scale up. We evaluate ARO on models from 0.3 billion up to 8 billion parameters, covering different architectures and overtraining regimes. This plot shows the speed-up comparison of ARO versus mu1 and AdamW. From this, we observe that ARO remains consistent advantages around 1.3 and 1.1 times over AdamW and mu1, respectively. As model size increases, we do not see the advantage shrinking at larger scales. All of the experiments use our efficient distributed ARO implementation. In our setup of 8 billion runs, the per-step runtime is on par with AdamW, meaning that the speedup translates directly into wall clock time savings. Overall, these results suggest that ARO speedup is scale robust. Based on this trend, it is likely to maintain its advantages over AdamW and mu1 as we move on to even larger models. To summarize, ARO is a general framework for matrix optimizer. It not only unifies many existing ones, it also provides design opportunities for novel and more efficient optimizers. Additionally, ARO can be easily extended and therefore incorporate new developments in the matrix optimizer community for further improvements. Our empirical verifications shows consistent advantages over both AdamW and mu1 across different model and data scales. Overall, we believe ARO is a competitive optimizer for training large model at scale. We want to thank all the collaborators in Microsoft Research and all interns for their valuable contributions, discussions, and feedback. If you are interested, please find the paper link in below.